All right, so let's pick it up again where we left off last time. This is chapter 2 now. So we're looking at applications of integration, and we're starting out with some physical applications. Specifically, we're going to be looking at areas and later on volumes that can be estimated from a function. And so we started out by looking at areas between curves. Now here, if you look at this graph, you'll notice we have some function f of x, and what we're trying to do is figure out the area between that function and the horizontal or x-axis between the interval a and b. Okay, now you might recall that from the fundamental theorem of calculus, this is nothing more than the definite integral of f of x dx over the interval from a to b. Okay, so in other words, we actually solve for the integral, and we'll have our area. All right. Now, what we're going to do next is extend this a little bit, so that what's coming up next is we're trying to look at cases where we had more complicated situations. Here's a perfect example of this. Suppose that we discover that what we're looking for in the graph here in the middle is not the area between f of x and the horizontal axis, but f of x and g of x. Okay, so that is not what we were doing before. So now we have to change our approach a little bit. So the way to think about this is that f of x, the blue line here, if you were to look at its area down to the x-axis, well, we know already from the fundamental theorem of calculus that what you have to do here to come up with this area is take the definite integral over the interval a to b. And if you look over here on the bottom right, g, it's a curve. And if we wanted to look at its area between g of x and the horizontal axis over the interval a to b, again, we would use the fundamental theorem of calculus, and we discover that we have the integral from a to b. So the clever strategy here is to say, well, why not calculate both of these and then subtract one from the other? Now, the graph here, what I'm trying to indicate is that if I calculate the entire area from f of x down to the horizontal axis, and then subtract off the area between g of x and the horizontal axis, what's left over is what we're looking for here. The blue shaded region is what we're actually after. Okay, so you can see then that all we're really going to do is subtract the integral of the what we'll call the top function. Or what I should say is we're going to take the integral of the top function and subtract the integral of the bottom function. And so right here at the bottom, what all this has been leading up to is that we are going to subtract f of x minus g of x over the interval from a to b. And we'll get our result. Okay, so now, but it's now, by the way, when we do this, it's understood that along the entire interval there, and again, let me try to reproduce this one more time. Let's say this is f of x, and we have g of x. So over the interval a to b, what we really want is this area. And so our approach will be, again, to take the integral of the so-called top function, the f of x, and subtract the bottom function, which is g of x, integrate over the interval a to b, and we'll have our result. So this is just an extension of the fundamental theorem of calculus. Now we have to be careful here. We have to make sure that over this entire interval, f of x is indeed above g of x. So this condition has to hold over the entire interval. Otherwise, we have to try something different. So let's take a quick look at the logic behind what we're doing. As we saw in the previous chapter, what we're essentially doing here is creating a series of rectangles. So let me make that bigger so you can really see it better. So in other words, the area that we're really interested in can be approximated as a series of rectangles where we have intervals from x1 to x2, x2 to x3, all the way up to xn. So it's understood that the width of each of these rectangles is the same, and we call that delta x. And it simply equals xi minus xi minus 1. In other words, if xi is 2, let's say, we subtract from that x1, the width between, or the difference between those two is the width. We want to make sure that those are all equal to each other. Okay, so we call that delta x. It is a constant. Now the heights, on the other hand, can be determined in one of two ways. You can either use the left endpoint or the right endpoint. If we do, we have to be consistent. In other words, if we're using the left endpoint approach, we have to always use the left endpoint. If we're using the right endpoint, we always have to stick with the right endpoint. So that asterisk there indicates that we've, in this example at least, we've chosen the left endpoint to calculate the areas of our rectangles. And you can tell by looking at these rectangles, they're all a little, up to about here. They're all just a little too tall for this region. In fact, in the bottoms, you can see they spill out just a little bit. And down here to the right of this line, they're a little too small. But the bottom line is, it's the left endpoint that's determining the height of each of these rectangles. Now, we saw earlier that ultimately, it doesn't make any difference whether we choose the left or the right endpoint. We will get the same results as we shrink up the size of the rectangles. In other words, as the number of rectangles increases, delta x decreases, and in the limit, both the left endpoint approach and the right endpoint approach will give us the correct area between the two curves. Okay, so what we're doing is exactly what we did in the previous chapter, except now we're thinking in terms of a difference. So the area is approximately equal to the heights of these rectangles, which represent the difference between the two curves, times delta x. And now what we're going to do is take the limit of this sum as n goes to, delta x goes to infinity, 0. N goes to infinity, delta x goes to 0. And that's what we're seeing here. And in the limit, we have the integral from a to b of f of x minus g of x dx. All right, so let's do one of these. It sounds a lot more complicated than it really is. Okay, so for example, let's take a look at this case. We've got two functions, which are both straight lines. And we'll see a graph of this in the next slide. We're interested in the area between the two lines over the interval 1 to 4. And this is what it looks like. Now, it's clear from the graph that over this interval 1 to 4, f of x is always greater than g of x. So we're good there. Okay, we can use this approach. We're going to integrate the difference between the two over the interval 1 to 4. By the way, in a case like this, a very straightforward case, if you wanted to, you could calculate this with geometry. I mean, it's pretty clear that this is a trapezoid, but why don't we stick with the integrals and take it from here? So we'll plug in the names of the information that we have. So we have f of x minus g of x. Then we drop the parentheses. So we have x plus 4 minus 3 plus x over 2 inside the brackets. We combine to get 3x over 2 plus 1. And now, as is usually the case, it's easier to break this up into two separate integrals. We'll have 3x over 2 dx and just plain dx. And then for the next step, what we usually try to do is move all the constants on the outside just to keep our formula as simple as possible. So here we've done exactly that. So we're going to have a equals 3/2 of the integral of x dx, and then we have the integral of dx. Now, a quick reminder here, the integral of x dx is just x squared over 2. If it's an indefinite integral, we add the c. Here we don't have to worry about that because this is a definite integral. For the dx, the integral of dx is simply x, and for an indefinite integral, this is x plus c. So now what we need to do up here in the upper right-hand corner is evaluate our results. So the 3/2 stays on the outside. So we'll have x squared over 2 evaluated between 1 and 4. And then we add to that x evaluated from 1 to 4. Now what I've done here too is I've moved this 2 outside just to keep things a little simpler. Okay, now we're ready. Right? So let's go look and see what this gives us. Okay, so this is where we left off right here. So this is what we're about to solve for. Now, by the way, I just want to quickly remind you what this notation means. When we have a box like this, x squared with a range of values, what this is telling us to do is calculate whatever this function is, or evaluate it when x equals 4, and then do the same thing for 1 and then subtract. Okay, so this first one is actually equivalent to saying 4 squared minus 1 squared. The second one is just asking us to do 4 minus 1. So we'll do that down here. We have 3/4, and then here we have 4 squared minus 1 squared. And then here we just simply have 4 minus 1. So we can rewrite this as 3/4 of 16 minus 1. In the second case, we just have 3. So what do we have? 3/4 of 15 plus 3, 45/4 plus 3. Now we need a common denominator. Let's convert this 3 into 12/4. And so ultimately we'll end up with 57/4. That's the area between the two curves. That's all there is to it. Okay, so it's a very straightforward idea. Now, the functions themselves can get very messy, but when they're not messy, they're well behaved like this, this is a very simple idea. Now, when can we run into problems, though? Well, I did mention that we have to make sure when we use this approach that f of x is really greater than g of x throughout the entire interval. What if that's not true, though? What do we do then? For example, how about this case? Now, I sketched this in before. It's not the best sketch I've ever done, but the solid line here is f of x. It's a curve. And then this dashed line down here is g of x. And what you notice right away is that between 0 and 2, this interval here, f of x is greater than g of x. But between 2 and 3, it's the other way around. So what do we do now? Okay, well, and by the way, this is sometimes called a compound region because it has areas where one function is greater than the other and areas where it's the other way around. So basically what we're going to do is treat each of these separately. We're going to apply the approach we just saw from 0 to 2, and then from 2 to 3, and then we'll add up the results. So in other words, we're essentially breaking this up into 2 problems. We'll do each of these individually, and then we will solve by adding them up. So over the interval from 0 to 2, we'll have f of x minus g of x dx. And then you'll need, over the interval 2 to 3, g of x minus f of x dx. So that's how you will handle this one. Okay. So basically it's the same thing, except that you're splitting up the regions so that you can treat them individually and then add up the results. All right, so let's look at a specific case. We're looking at f of x equals x squared, which is, of course, a parabola, and g of x is 2 minus x, which is a straight line. And we're interested only in the interval from 0 to 2. All right. Well, actually, I'll tell you what, let me do this. I'll put a new copy here just so that it's easier to see. Maybe I can make it a little bigger while we're at it. So you can see now they're going to cross, given that one is a straight line and one is a parabola. So the area we're after is 0 to 2. Now, what is important, you can see they cross. Here. Now, in this particular case, the so-called bottom function is actually the horizontal axis. So we're not really comparing these directly to each other this time. Now, from 0 to 1, if you notice, f of x is below g of x. Okay, red is below blue. From 1 to 2, it's the other way around. So this is definitely a compound area. So what we're going to do is, as we saw before, from 0 to 1, we'll have g of x minus f of x dx. And then from 1 to 2, it's the other way around. By the way, how can we prove that 1 is the intersection between these two? It looks like it on the graph, but it's not really a good idea to make assumptions based on a graph. So what we're going to do is this. Okay, so once again, f of x is x squared, g of x is 2 minus x. So how do you know where they intersect? Well, you just set them equal to each other. Okay. X squared equals 2 minus x. Actually, I don't need parentheses, 2 minus x. Now, of course, I want to get everything on the left-hand side. I'll add the x, subtract the 2. So this is a quadratic equation. It will have two solutions. We can use the quadratic formula, or in this case, we can just factor. And that implies that x plus 2 equals 0 and x minus 1 equals 0. X minus 2, or x equals minus 2, x equals 1. So there's going to be 2 points where they cross. So I've sketched those in on the next slide. And you can see, yeah, at -2 and 1, in both cases, the two functions cross. But remember, we're only interested in the interval from 0 to 2. So we can just basically ignore the -2. Within the interval of interest, from 0 to 2, the functions cross at x equals 1. And that's how we'll set up our problem. We'll integrate from 0 to 1, and then again from 1 to 2, and add our results to come up with our final answer. All right, so let's do that. So I've drawn it again. It looks okay, I guess. So here's the two functions. So we're going to call this first, the black region is A1. The book uses the notation. The first region is called A1. Its area is A1. The second region is A2. Okay, so A1, as you can see, now within that region, now keep in mind what we're trying to do here. We're interested in the area from f of x down to the horizontal axis. So while you notice how it's written like this, even though g of x is on top, within this region, the lower function is actually the axis. So you're actually going to just subtract off 0 there. Okay. So in other words, we're not looking at the actual area between the two functions. The way this thing has been set up, we're only interested in the area between the individual functions and the horizontal axis. It would be different if we're looking for the areas between them, but instead we're looking at the area between, from 0 to 1, we need f of x minus the axis. And so that has a value of 0. Okay, in other words, the horizontal axis has a value of y equals 0. So if you notice here, I've just got f of x here, and I'm not subtracting anything. I'm actually subtracting 0. So I'm taking the integral of x squared over the range from 0 to 1. That, of course, is x cubed over 3, evaluated from 0 to 1, which means 1/3 minus 0, and that leaves me with an area of 1/3. So the black shaded region, which we're calling A1, is 1/3. Now for the red region, which we're calling A2, the function on top is the g of x, 2 minus x. The function below it is actually the horizontal axis. So based on this logic, what we're going to see here is, even though it's written like this, we're going to have okay, and g of x was 2x minus 0. And oh, by the way, also don't forget, this is the red region. This is the area from 1 to 2, okay? Only from 1 to 2. All right, so what we're actually going to wind up with here is this. Okay, and you just plug in minus x dx, and then you come down here. We'll break that up into 2 pieces, 2 dx minus x dx, and then we evaluate. Now, this one, oh, sorry, 2 dx. That would be 2x plus c if it were an indefinite integral. And of course, this one here, x squared, x, just plain x, would be x squared over 2. So anyway, when we evaluate these, we have 2x evaluated from 1 to 2, and we subtract from that x squared over 2 from 1 to 2. Now we just plug in some numbers. Okay, so I've copied that into the next slide. So this is our starting point. What do we do here? All right, well, for the first one, we have 2 times 2 minus 2 times 1. In the parentheses here, we have 2 squared over 2 minus 1 squared over 2. So this reduces to 4 minus 2 minus 4 halves minus 1 half equals 2 minus 3 halves, or let's rewrite this as 4 halves. And so ultimately, area 2, the red area, is 1 half. Okay, now we just add it together with A1, and the total area that we're actually interested in is the sum of A1 plus A2. All right, so there it is again. This time, I guess I should have used red to be consistent here. You get the idea. Okay, so that's our final answer. We have a half and a third. So this whole area, the combination of the red and the black areas, adds up to 5/6. Okay, now there's another potential wrinkle here. If you notice, so far all the examples we've seen, we're looking at an intersection between 2 curves down to the horizontal axis, or maybe between 2 curves without the horizontal axis being involved. But what if we're not interested in those areas? Suppose instead we get something like this. And instead of being interested in the area down to the horizontal axis, what if instead we're looking for this area? Ooh, in other words, the intersection between the two over to the vertical axis. That's possible too. Okay, there's no necessary reason why we only would care about areas under the curves. Maybe we're also interested in areas to the left of the curve. Well, it turns out we're going to actually end up using very similar steps to solve for this, except we have to think of all these functions in terms of y instead of x. That's essentially the only thing that will change here. Okay. So for this one, we'll rewrite f of x, g of x as functions of y, which we'll call u of y and v of y. This also means that the limits of integration will also be changed. Okay, but once that's done, everything works the same way. All right, so we can also integrate with respect to y rather than x. So in other words, the formula will look a little different. Okay, now remember before, and of course it depends. And also I just want to remind you too, instead of thinking about top and bottom functions, we're going to have to think about left and right functions. Okay, that's another consequence of this. Instead of thinking in terms of tops and bottoms, we have to think about rights and lefts. In other words, the top function, the bottom function, or the right and the left. Okay. Now, it's entirely possible that the left itself will be the vertical axis. Okay. Like we saw that with the horizontal axis. Sometimes we're just looking at two functions. Sometimes we're looking at the difference between a function and the horizontal axis. So we have to just adjust our thinking, but the actual technique won't change. Also, I just want to point out, just to make sure it's clear which is which, they're going to use for the limits of the integration, instead of A and B, they're going to call it C and D. Okay. It's just to help remind us that they're probably different. Okay. So in other words, instead of this, we have this. All right, now we're going to take a familiar friend here, and we're basically going to flip it to look at the area not between the functions and the horizontal axis, but the vertical axis. So basically what we're doing now is looking for this shaded red region, basically. Okay, in other words, instead of blue, we're looking for red. Now, just by ridiculous coincidence, it looks like the limits of integration are the same, but that doesn't always work out that way. All right, so let's see what we're supposed to do here. Oh, you know what? One more thing. I just realized I didn't mention this. It looks like we're, I see. Yes, you see now, what's happening here is that we're actually only interested in this piece. So Yeah, I didn't write that as clearly as I could have. Yeah, see, it does say the words intersection. It wasn't as clear as I think as it could have been. In other words, it's the region bounded by the two functions, the x, that's the, sorry, that should say y. And the intersection between f of x and g of x, which occurs on the vertical axis at 1, just like it did on the horizontal axis. So this is what they're really looking for right here. That should have been written more clearly. But anyway, with that in mind, what we have to do first is take the existing functions, and it doesn't really matter which one becomes u and which one is g. Let's just say the f of x becomes v of y. Just remember that f of x equals x squared is the same thing as saying that y equals x squared. G of x equals 2x is the same thing as saying y equals 2 minus x. Therefore, what we're going to do is write x equals v of y, and that means what you're basically doing here is solving for x. Okay, so, and by the way, since we're only interested in the second quadrant, we don't need to worry about the fact that when you take the square root of x like this actually results in both plus and minus radical y, but negative radical y will not appear in the second quadrant. So we're only interested in x equals radical y. Now over here, we took y equals 2 minus x, and what we're doing is we're solving for x. And that will now become known as u of y. So we now know that u of y is 2 minus y, v of y is radical y. Okay, so let's look at the graph again. And here I demonstrate why x equals 1 is the point where they intersect. So what this is telling me is that the limit of integration, remember it's C and D, this is C, rather, this is C, and this is D. So this corresponds to A and B when we're using the x-axis. Okay, so there's the integration that takes place will occur over the interval from 0 to 1. All right, so with all that being said, let's do this. So, let me do this real fast. Let me sketch it in one more time. But in terms of y, so now this curve, which is, we originally called it f of x equals x squared. Remember now, we're writing it as so in other words, with respect to the y-axis, this is the square root of y. And then the other one, we've already seen that u of y is 2 minus y. They cross at this point. We're interested in this area. So here's what we're going to do. By the way, if you look at it carefully, you'll see that within the range that we're interested in, this function could be considered the right function. And then this one could be considered the left. Because only within that interval, you can see that u of y is always further to the right than v of y. And so what that implies is that when we set this thing up, we'll have u of y minus v of y dy. And if you did it backwards, you would just get the right number, but with a negative sign. Okay, so anyway, let's just see how that works. So once we got that straightened out, this is what we just did. We'll just make the substitutions. This is again u of y. This is v of y. Now this is going to be interesting. Well, actually, we've got 2 minus y minus radical I when we drop the parentheses. We can break this up into 3 intervals, 3 straightforward intervals. Bear in mind that radical y is 1 to the 1.5. Okay, so this first one, you'll have 2y evaluated from 0 to 1. This one will be negative y squared over 2 evaluated from 0 to 1. And finally, this one will be y to the 3/2 over 3/2, 0 to 1. Now I'm going to move out the constants. Here, remember, dividing by 3/2 is the same as multiplying by 2/3. Now we just evaluate, for example, oh boy, that was so close. I just barely squeezed it in there. But this is on the first line of the next slide anyway. I just wanted you to see what I've done. So remember, you're evaluating over the interval from 0 to 1. So you plug those in, and now you just solve. Here we have 2 times 1 minus 1/2 of 1 minus 2/3. This is just 1. So you got 2 minus 1/2 minus 2/3. And of course, the best common denominator here would be 6. So you've got 12/6 minus 3/6 minus 4/6 equals 5/6. And that, by the way, if you notice, it was just a ridiculous coincidence, but it was the same area that we had earlier when we looked at the x-axis. It usually doesn't work that way. Okay, it's just the way the functions are laid out. But yeah, it was just a coincidence. All right, now now that was 2a, by the way. 2a is this separate section. We're only looking here at areas. Now, what's coming up next is we're going to move into another dimension, literally, because we're going to now consider volumes. Yeah, that's right, volumes, which means 3 dimensions. And that's, of course, going to make things more complicated. So there's a series of techniques that we can use to find the volumes of different types of shapes, different types of solids, I guess we should call them. This is the kind of thing that would really come in handy if you were involved with graphic arts or of some kind, trying to design, you know, or architecture, even trying to figure out, for example, what would be the volume of that something that you're trying to create, but you're not going to run into any of this in any business related application. But certainly in physics, engineering, architecture, any discipline involves physical objects, this could be very useful. Okay. By the way, what's going to come after that is other applications. It's not all about areas and volumes. But anyway, we're going to be looking at volumes. Now, there's different ways we can go about this. The approach they take is actually kind of clever here. So first things first, we want to remind ourselves about some basic shapes that you haven't probably thought about for years. We have spheres. And you can think of a sphere as essentially a circle that's been rotated on the axes. Now, I can't possibly draw that properly for you, but if you could imagine spinning this thing on the vertical axis, it would fill in to create a sphere rather than a circle. Then we can have a cone. There are different kinds of cones. The kind we're looking for here would be something like this. All right, well, that's not perfect, but you get the idea. And there's the height. Okay. One of the variables we need to calculate the volume of this pyramid, cone rather, is the all right, that'll have to do. And then, of course, the pyramid, well, now we're talking. Oh, okay, that will have to suffice. All right, but anyway, what we're going to do here is quickly review some of the formulas. The volume of a sphere, which you probably had to memorize at one time, is 4/3 pi r cubed. Of course, this is the radius. Going all the way across would give you the diameter. So this is usually expressed in terms of the radius. 4/3 pi r cubed. Where, of course, the 4/3 and the pi are just constants. The cone, like I was saying, this one, you need to know the so-called height. Which means you're taking the peak and connecting it to the base, which is a circle, by the way. And this is your cone. 1/3 pi r squared h. Now the pyramid, that's a tricky one. I have some graphs in there that I copied out of the book because I couldn't possibly draw them. But what's different here is that the base is a square. That's what really separates it from the cone, rather. And so you're going to have a height, just like the cone. What's different is that the base is a square. And that A is the area of that square, or the base. Okay, so those are some of the standard solids, they're called, that you might run into with these applications. Now, what we're going to do is introduce the concept of this cross-section. Cross-section is kind of like slicing a loaf of bread. Oh, if only I could draw better. Well, that's not too bad. Okay, so in other words, a cross section would mean imagine I take a knife and cut right down through the bread, and what results in 2 dimensions is this. Okay. Uh, wow. So I'm slicing it with the cleaver, let's say, and I break it, take it apart, and now I'm looking, this is my cross section. So I'm trying to cut it, so it looks like slices of bread. They're technically known as cross sections. Each slice of bread is a cross section. So here's a much better graph. This is sort of like a half of a cylinder, the top half of the cylinder. And so the plane that slices through this creates a cross section, which if you flip it around towards you, it will look like this. So the strategy here is that to figure out the volume, what you're effectively going to be doing is calculating the areas of these cross sections many, many times and adding them up. Luckily, we have formulas for most cases, not always, but to do these directly. Now here they're giving us a very challenging one. I don't know if there's even a name for this thing. They're going to just call it a solid. But what they're trying to get at here is that just like when we were doing integration, let's start with 0. And what we were doing initially was coming up with the heights of rectangles. And let's say we're using the right, the right endpoint method. Well, something similar is happening here is what I'm getting at. And then here's delta x, delta x, delta x. They're doing the exact same thing here. But what's different now is that each of these slices has itself a volume. Whereas with these rectangles, we're adding up areas. Okay? So here, each slice has a volume. And the volume comes from, by the way, if you notice, each one of these has a different cross section. Like that first one back there. The back part is the cross section. Okay, so they each have a cross section. So the volume of each one equals delta x times the area of the cross section. So you can see this is what's making this a different, well, this is the difference between what we're doing now and what we were doing before. Before we were looking at areas of rectangles. Now we're looking at volumes of slices. And then we're going to have same way, except, and of course, as you can imagine, we're going to take the limit as the number of slices grows to infinity to come up with the correct volume. So we're going to use, and by the way, just like with our integration over the horizontal axis like this, within each interval, there's one of the 2 points is the one that we're using for each case. In other words, we had the left point method and the right point method. We have something like that going on here, and whichever one we choose is designated with an asterisk. So here I was trying to draw it with the right point method. So that means within this interval, it would be designated like this. Anyway, so that explains the notation you're about to see. The volume of the slice, as I just said, this is the area of the cross section, and is defined in terms of xi star, and this is of course the width. Now, the volume of the entire solid is the sum, or is approximately the sum of all the slices. But if you notice, they're using the approximation sign because just like with integration, those rectangles. Oh boy, what happened?
Always happen. And
I have no idea what just happened. I must have a website open that has an obnoxious commercial on, but I can't find it. Oh, I think I got it right there. No.
Always happen. And always will be. So check the label for cotton. And
there we go. I got it. Usually ESPN is the culprit. If you ever look at ESPN, if you leave it on for any length of time without looking at it, almost without fail, it's going to suddenly start an obnoxious loud commercial on you. So you have to be careful not to leave it on. When you're done reading ESPN, always turn it right off. I've actually had it wake me up in the middle of the night because it was doing that. You got the laptop sitting there, and all of a sudden this wretched ad comes on, and you're looking around like, what's going on? And then all of a sudden you realize it's just a stupid ad on your computer. Oh, well. Anyways, so the areas of these rectangles are only approximately equal to the true area under this curve when we have wide, very wide rectangles like that. It's only as we converge to the limit that we reach the actual area under the curve. And the same thing is happening here. In other words, in this graph, we've only got the 3 slices. So the area that we need is only going to be approximately equal to the sums of the volumes of those slices. And we keep shrinking up the delta x's and add them together with an interval. Eventually, we'll reach the correct volume. All right. And there it is. In other words, this is the approximation, as you can probably guess. But the exact area comes from taking the limit. Now, you notice n goes to infinity means the number of slices is approaching infinity, which implies that delta x is approaching 0. Okay, more slices means each one is less wide, and so therefore in the limit, n is approaching infinity, or equivalently delta x is approaching 0. So you end up with what we're looking for. So basically the strategy with any volume is to figure out the correct cross section. Remember, the whole thing is based on the area of that cross section. So this will work well for well-defined volumes. Like a sphere, for example, each cross section would simply itself be a circle. Okay, and so it would be easy to figure that one out. All right, now, by the way, this technique is actually called slicing. All right, the slicing method, because the slices are what gives us the cross sections. And again, I love my analogy of cutting through the loaf of bread, so that each loaf, sorry, each piece of bread is a cross section. Okay. So with all that being said, let's look at a pyramid. Now, this is not a simple example. It's going to take a bit to follow along with it. But like everything else, once you've done a few of these, you'll see that it's really not that complicated. But it does take a lot of getting used to, especially for these very complex solids. Like I said, it would be very simple with a sphere. But we'll start with a pyramid. Now, the book is showing it to us in two different ways. First, they're sort of tilting it to the side so you can see it as a three-dimensional figure, and then they're just giving you what amounts to essentially a two-dimensional picture of the same thing. And because it's defined with respect to the origin, you could think of it as a pyramid that's laying on its side. Okay, in other words, this is the base. And this is the height. Oh, it's there, right? Now, what they're going to do here is use a little geometry, by the way. If you haven't seen geometry in a while, I just want to remind you about this, something very important, which is that when you have two triangles, and let's say here's your two triangles. The angles are 30, 60, 90. It's a 30, 60, 90 right triangle. The sides are 1, 2, radical 3. And then here's another one. 30, 60, 90. But this one is clearly bigger, right? So let's say this one is let's see, how would that look? No, let's do it this way. Oh, let me get out my calculator. I have to make sure I'm planning this correctly. Yeah, this is fun. 2 radical 3 and 4. You can tell it this is right because remember our old friend, the Pythagorean theorem tells us that a squared plus b squared equals c squared. Okay, anyway, what is the point of this? So let's say this is triangle A and this is B. So what happens here is that A and B are similar triangles. And so what that tells us is that the proportions of the sides are the same. So specifically, the ratio of the height to the base, think of this as the height and the base, has to be the same. Because one is essentially just a bigger version of the other. Okay, so with that being said, if we go back to this graph, now they didn't label these. Let's say this is triangle A, this top part. And the entire thing is triangle B. Okay. So what they're trying to get at here is that if you look at them carefully, the angles are all the same for both triangles. And in fact, the angle at the vertex, the peak, is the same for both of them. So A and B are similar triangles. Now, if you notice, for triangle A, the height is X. And oh, it may be hard to see it in there. There's an S in here. So the height is X. The base is S. For triangle B, the height is H. And the base is A. So because they're similar, that implies that X over S equals H over A. They're similar triangles. They must have the same ratios. Well, how does that help us? Well, let's find out. Okay, so the two ratios are the same. And that means, and by the way, remember what we're trying to do here, we're taking a pyramid which has a square base. The area that base could be defined as the cross section. So therefore, what we're trying to figure out here is S. Okay, the dimensions of the base of this small triangle. So S, rearranging it algebraically, you can just cross multiply them and you'll see what happens. XH equals SA. Oops, I did something wrong. Ah, no wonder I copied it wrong. That doesn't help. All right, and these are the same thing, of course. Now remember too, what we're really after is the area of the space. So that means the area that we need is S squared, A squared, X squared over H squared. So let's write that down again so we don't lose it. S squared. Now, by the way, of course, at the moment, we don't have the specific values. A and H are constants. They have to be given to you. X is the only variable here. So given what we just saw, the area of this pyramid, or the volume rather, is going to require us to go over the interval. And again, they haven't given us the exact numbers. So think of this as 0 and H. So in other words, the interval is over, the integral is between 0 and H. So that's where they're getting these. And now you recognize this piece is simply S squared. That's what we're looking for, the area of the cross section. Now, of course, this is going to be treated like any other integral you've ever seen. This is a constant. We move it outside. So we're integrating x squared dx over 0 to h, which now, of course, the integral of x squared is simply x cubed over 3. So this is it. Now we can take it further by substituting h into there. But that's as far as we can go without some actual numbers. Okay. All right, so let's do that. Let's bring it to the next slide. Let's just see what that looks like. So this piece by itself. So you've got this constant. Oh, by the way, you know what I just realized? I forgot to point this out. This 3 got moved outside. I forgot to mention that. That's better. So in other words, you might have wondered what happened when we jump to the next slide. That's why this is written like this. And then this part by itself is equal to h cubed. So you've got a squared h cubed over 3h squared, or just this. So whatever the height is, and of course you also need to know a. Once you know those two values, you can figure out the volume of any pyramid. Okay. So, well, that was quite an ordeal. Now, what's coming up next is even a little bit more involved. What you have to visualize, what's coming next, is what we're going to create is something called solids of revolution. Now, this is going to be very difficult to draw properly. If you can imagine, wow, I'm not sure if I can do this. I'm just going to jump ahead and show you a picture taken from the book. I really don't think my drawing skills are up to this. Let me show you an example of what we mean by a solid of revolution. So you got this normal curve, and you see how we're looking at the area between the curve and the horizontal axis. We've seen this before. What they're going to do is say, just imagine if you take this thing and rotate it about the x-axis. It's like, if you ever, I don't know if you've ever seen pottery being made. I think this is a good analogy where they put clay on this big wheel and it spins around, and then they spin it with their feet and they hold it with their hands, and they just sort of, I don't know, all of a sudden, right before your very eyes, it turns into a pot or something. It's just uncanny how it goes from this big blob of clay, which is beautiful shape. And so you're doing something similar to that. You're spinning it around, and all of a sudden you have this. That is what we mean by solid of revolution. Wow. So now you probably can't imagine that we can figure out its volume, but actually we can. The reason why we can is because we have the function. This top red line is f of x, and we know the height of this line. So even though this isn't one of our standard shapes, it's not a pyramid, it's not a cylinder, not really. I mean, it's not what we call a right cylinder, which is basically a Coke can. It's a type of cylinder, but it's not a standard one. So in other words, there may not be a formula for this thing. There probably isn't. And yet, in spite of that, we can still figure out the volume. Okay. So that's what's going to occupy us in our next section. How to solve the volumes of these solids of revolution. It's actually just a fairly straightforward extension of what we did here. It may not seem like it. The only thing that will be different is the formulas that we use don't have to conform to a standard shape, basically. But the logic is exactly the same. So it's really just more practice with the same concept. So anyway, so I think because this is a fairly complicated topic, we probably should cut it off right here and relax and recover for a bit. And then we can carry on with this next time. Now, after this, we move into other types of applications. So in other words, geometry will go by the wayside after this, and we'll get back to straight ahead calculus. So anyway, so I'll see you all next time.